गुड मॉर्निंग साहिल. आवाज येतोय का सांगा मला फक्त एकाने कोणी. यश. अथर्व आवाज येतोय का?
हो सर.
व्यवस्थित येतोय ना?
हो.
एक मिनिट परत सांग बरं मला. येतोय आता?
हो येतोय.
ओके. स्क्रीन दिसतीये का?
हो सर.
ओके, सुरू करायचं आपण.
येस.
So in this solid state chapter, already I am telling you again and again the weightage is reduced. So whatever the important part I am giving to you, only prepare that part because this chapter is very big and the weightage is very small. So I think in this packing part is covered. No any bigger question will be asked for this packing. So don't worry about this packing because many students calling me again and again, sir, this we didn't understand this packing. So in this, whatever the packing part is given, this one dimension, two dimension packing, it is not asked for the examination, but only remember the coordination number. What is mean by the coordination number? It is nothing but any one square, any one sphere that touches to the given sphere. Suppose this particular sphere is taken, I will show. See, if this particular sphere is taken, this sphere touches to another two square, so the coordination number is 2. Then this is applicable to any square in the packing. So there are hexagonal close packing is there, then a square close packing is there. We already discussed about these square packings. This is square close packing because all these spheres are same. A type of arrangement is there. So here the square is obtained and the coordination number is 4. Then also we discuss about this hexagonal close packing in this is AB type of arrangement because in the depression of the A layer, a B layer is kept. So the packing is again close packing is there. See the space, more space is utilized, and see this empty space is more here in case of square close packing. So this empty space again it is utilized in hexagonal close packing. The coordination number is 6 because here we can see the hexagon it is obtained. We can see the hexagon is obtained and the coordination number is 6 because any sphere it is in touch with 6 pairs. So this is about the one dimension and two dimension close packing. In case of three dimensional close packing, AA type of arrangement, the coordination number is 6. This is a three dimensional AA type of arrangement. We also prepare such kinds of models. by using the small balls. So in this three-dimensional square close packing, all the spheres are AA type of arrangement. Only above this, we are putting another layers. This is also the second layer, third layer, fourth layer. So the main important thing of this closed dimension, sorry, closed packing in three-dimensional, the coordination number is 6, because any sphere, it is in touch with 6 pairs. Four is in its own layer, and one is above and one is below. So polonium is the only element that crystallize in simple cubic close packing. Remember, this can be asked for the MCQs. So remember this polonium, because it is having more chances to ask for the MCQ purpose. Which of the following element crystallizes in simple cubic close packing structure? In case of hexagonal close pack structure, there are two types of voids are prepared. Voids means empty spaces are prepared. Tetrahedral void and octahedral void. So I will show when the tetrahedral void is prepared and when the octahedral void is prepared. We have to see this diagram. When such type of situation is there, when the three spheres are behind and only one sphere is above. So here we can see clearly, see here we can see this tetrahedral void is prepared, because this is the first layer, this is the second layer, again there will be third layer, fourth layer. So we will get the three-dimensional close packing structure here. So here, when such type of situation is there, when the three spheres are behind and only one sphere is above, we will see this is the tetrahedral hole is prepared. We can see here tetrahedral holes, these are already covered. And when this situation is there, when the three spheres are in the first layer and the three spheres covered in the second layer, so such type of void, this is a octahedral void. This is also the octahedral void. This is the tetrahedral, tetrahedral, tetrahedral. Again, this is a octahedral, octahedral, octahedral. Again, this is a tetrahedral, tetrahedral. This is octahedral, octahedral, octahedral. When such type of situation is there, octahedral holes are created, or it is also called as octahedral voids are created, and tetrahedral voids are created. So actually, this is a not asked for the examination for the drawing purpose. No any examiner will ask the question, draw this octahedral void or tetrahedral void. Only they will ask the question in case of three-dimensional closed packing structure, which type of voids are prepared. So don't give much importance to these diagrams, only for the understanding. These two diagrams are same, only it is shown with colored balls, and this is shown with only circles. So this diagram and this diagram is actually shown. For the understanding purpose, I have shown these two diagrams. Whatever the diagram you understand, we can follow. So I am not wasting much time in close packing structure, because we have to also, this is a uh, when the third layer is kept in case of AB type of arrangement. So this is the first layer, this is again second layer, this is third layer, this is fourth layer. So this is AB type of arrangement. So if AB type of arrangement, it forms the hexagonal close packing structure. We can see from the top view. So this is the top view, it is shown. This is A, this is B, again this is AB. So this arrangement will continue, and we can also calculate the coordination number here. So the coordination number will be, it will be 6 plus 3 plus 3. Coordination number will be 12, because if you can see this hexagonal close pack structure, in the first layer, the coordination number is 6. Then in the second layer, three spheres will touch. In this diagram, we can clearly see. So the coordination number will be 6 here, the coordination number will be 3 here, and again the coordination number will be 3. So Each sphere is in contact with 12 spheres. So the coordination number will be 12 in this both the arrangement. This is a AB type of arrangement, and this is ABC type of arrangement. When this ABC type of arrangement is there, we get this is a cubic closed pack structure, and when the hexagonal arrangement is there, we'll get hexagonal closed packing structure. When sorry, AB type of arrangement, we will get the hexagonal close packing. And when ABC C here, C is a different layer. In this, so we can see this is A layer, this is B layer, this is C layer, again ABC. So this will be continue. So if such type of arrangement is there, ABC, we will get close packing structure. And if AB type of arrangement is there, we'll get the hexagonal close pack structure. So this is only important for the MCQ purpose. Don't do in details, because this is quite confusing to understand, because the models, we have to prepare the models for understanding this close packing structure. Only I will tell you these examples, because for the examination point of view, these examinations are important. Uh, So this manganese zinc have the HCP closed pack structure. This is hexagonal closed pack structure, and this copper, silver have the CCP or FCC. It is called as also FCC, face centered cubic structure. So remember these examples: copper, Ag, and manganese and zinc. So this is important for the examination purpose. So directly, this is also coordination number is given. Already I discussed about this coordination number is 6 and 12. This is also important for the MCQ purpose, number of voids per atom in HCP and CCP. There are two tetrahedral and one octahedral void per atom. Remember, this is per atom. Now I'm coming to the packing efficiency for the 1 mark or 2 mark for the MCQ or answer in one sentence. This packing efficiency definition can be asked. So packing efficiency, it is nothing but it is the percentage of the total space occupied by the sphere. Remember, this is the definition of packing efficiency. Packing efficiency is the percentage, always it is shown in percentage of the total space occupied by the spheres, means how much sphere is occupied by the spheres, or it is also called as particles, you know. So in case of simple cubic unit cells, we can see the packing efficiency is 52.4, means 52.4% space is occupied. In case of body centered cubic, we are discussing with the cubic system only. We already discussed in case of cubic system, there are three types. First one is primitive. It is also called as simple. Then it is also called as simple cubic. So in simple cubic, the packing efficiency is 52.4, means this much space is occupied. In case of body centered cubic, see the space occupied is 68% space is occupied. You know, at the center of the body, there is one particle. And in case of face-centered cubic, it is also called as cubic close packing structure or hexagonal close pack structure. See the space occupied is 74%, but for the this year, this will be not asked for the examination. This is a non-evaluative. This is a non-evaluative part. This is deleted, so it will be not asked for the examination. We are only discuss with this simple cubic and body-centered cubic structure. So only this will be asked for the examination. So before proceeding, you must understand what is the definition is already discussed. What is the formula? How to calculate the packing efficiency? So packing efficiency is equal to the volume occupied by the particles in the unit cell divided by total volume of the unit cell. Remember, means you are calculating volume occupied by the particles in the how many particles which are present in the unit cells, and what is the total volume of the unit cell into 100. So one by one we will discuss. One will first we will discuss the packing efficiency of the simple cubic lattice. So in case of simple cubic lattice, A is equal to twice ER. We can see here, this is A, it is edge length of the simple cube, it is A. So A is equal to twice R. This is R and this is R. So R is equal to A divided by 2. This is the radius of the sphere. Radius of the sphere is A divided by 2. Then the second step, we have to calculate the volume of a sphere. You know what is the formula for the volume of a circle is 4 divided by 3 pi r cube. This is a volume of a sphere. So volume of one particle, it will be 4 by 3 pi r cube. We have to put this value of r in this equation. So r is a by 2, a by 2 cube, it will be pi a cube divided by 6. This is volume of one particle. This is a now we have to calculate the total volume of the particles. You know, in simple cubic unit cell, there is only one particle, so this volume will be remain same. So this volume will be remain same. Now we have to calculate the packing efficiency. You have the formula of the packing efficiency, volume occupied by the particle in unit cell divided by total volume of the unit cell into 100. Now we have to put these values. Volume occupied by the particle in unit cell, it is a pi e cube divided by 6. So this value is uh, inserted here. Then total volume of the unit cell, it is a cube. You know this a cube, this is edge length cube. So this is the total volume occupied by the unit cell into 100. By doing the calculation, we will get this answer 52.36. So this calculations can be asked for 2 marks. Calculate the packing efficiency of simple cubic lattice. So we have to write all these steps for 2 marks. This is for half mark, this is for half mark, this is for half mark, and this is for half mark. So this many times this is asked for the examination. Calculate the packing efficiency of simple cubic lattice. So we have to remember all these steps. And this is asked for the MCQ purpose. What is the space occupied by the simple cubic lattice and what is the empty space? So if you know the space occupied, 100 minus this space occupied, we will calculate the empty space. So remember these values for the MCQ purpose. And this is also asked for 2 marks. Calculate the packing efficiency of simple cubic unit cell. Now I am discussing about the packing efficiency in case of body centered cubic lattice. You know, in body centered cubic lattice, as at the center of the body there is one particle. So the total particles in case of simple cubic unit cells, there are two particles are present. The situation is different here, and the situation is different in case of simple cubic unit cell. So uh, how to calculate the packing efficiency of this body centered cubic lattice? For a triangle, see this diagram is shown here. If it is asked for the examination, also we have to draw this diagram. So for triangle FED, see this triangle FED. In this triangle, angle FED is equal to 90 degrees. See this angle FED means this angle we can see. See, this angle is 90 degrees. Yes. So in this triangle FED, the angle, this angle is 90 degrees. So you know, according to the uh, Pythagoras theorem, FD square. This FD square is equal to, this FD square is equal to FE square, this FE square plus ED square. So, this is a actually, FE and ED. This FE, this FE side, and this is ED. This ED is equal to A. So it will be A square plus A square is equal to twice A square. This is according to the Pythagoras theorem. Again, we have to discuss with the second triangle AFD. So here is AFD, this triangle. See this triangle AFD. I will show with this red color mark. So this angle A, see we have to consider this triangle AFD, this one. So in this AFD angle ADF, see this is also 90 degrees. So this is 90 degrees. So AF square, this is diagonal, AF square is equal to AD square, this side AD square plus FD square or DF square. So again, we have to substituting the equation 1.8 into 1.9. This is equation 1.8 and this is equation number 1.9. So AF square is equal to A square. We have to put these values. A square is equal to A square plus twice A square is equal to thrice A square. Because FD is already twice A square. See here, FD square, FD square, we already know about the FD square is having the twice A square. So this twice A square, it is value is taken here. So this twice A square and this is A square is equal to thrice A square. So if you have to calculate the value of AF, we have to take the square root of this 3A square. So AF is equal to under root 3A. In figure 1.10, this is a figure number 1.10, shows that AF is equal to 4R. See this AF, this is 1, 2, 3, 4. So this is 1R, this is a 2R, this is a 3R, and this is a 4R. So this AF is equal to 4R. AF is equal to 4R. You know this value of AF. So by substituting the value of AF in this equation, uh, under root 3A is equal to 4R. Under root 3A is equal to 4R. Hence R is equal to root 3 divided by 4 into A. We have to remember this equation. This equation, it is required for the numerical purpose. Also it is given in the tabular format, it is also given. So value of R is known now. Now you can calculate the volume of a sphere. Volume of a sphere, volume of a sphere formula is 4 by 3 pi r cube, and the value of R is also known. So by putting the value of R under root this value, root 3 divided by 4a. So this value of R, it is substituted in this equation. By mathematical calculation, we will calculate this is a volume of one sphere. So volume of one sphere is different in case of simple cubic, in case of body centered cubic, because the value of R is different. So this is a volume of a sphere. Now volume of a particles. As there are two particles in case of body centered cubic cell. All the corner particles form one, all the corner spheres, they form one particle, and at the center of the body, there is one particle. So there are two particles. We already discussed how these two particles are formed. So if this is a volume of one particle multiplied by 2, we have to multiply by 2 here. So 2 into this is the volume of one sphere. We will get uh, This value root 3 pi a cube divided by r. Now we have to calculate the packing efficiency. You are having the formula of packing efficiency, volume occupied by the particles divided by total volume of the unit cell. So this root 3 pi a cube divided by 8 a cube into 100, we'll get this 68%. So 68%, this is a volume occupied by the body centered cubic cell, and 32%, this is a empty space. So we can calculate the empty space by 100 minus 68, we will get here 32%. So these values, remember these values for the MCQ purpose: 68, 32, and face centered cubic unit cell. This is not for the examination for this year due to the COVID. This is a deleted part, so this will be not asked for the examination. So in this table we have to remember these two values. In case of simple cubic unit cell, a body centered cubic cell, this is the value of r, it is calculated. This is the volume of one particle, and this is the total volume occupied by the particles in unit cell. So these values we have to remember, and this is for numerical purpose. These values are required. Forget about the FCC. FCC, it is not for the examination for the due to the COVID situation. So only we have to remember these values. 0.500a. We have to prepare this chart. So I request you today, for solving the numericals, we have to remember this chart. Without remembering this chart, you can't solve the numericals. So this is already discussed, number of particles in the unit cell. This formula is already discussed here. I will show where this formula, we I want to erase all the marks. I will show where you studied, because two times it is given in the textbook. See this one, relationship between molar mass density. Uh, this is the relation between molar mass density, then age length, and this is a number of particles, Avogadro's number. So rho is here density, n is number of particles, then m is molar mass, and a is age length, na is Avogadro's number. So this relation is again repeated here. Only it is taken in number of particles of unit cell in x gram of metallic crystal. Already we discussed this formula. Already you know about this formula. So if n number of particles in x gram of metals, uh, we have to remember this formula. We have to remember this formula, but it is not required. By using this that formula also we can solve the numericals. We will discuss the numericals. We will discuss one numerical here. See here. First we will discuss this numerical problem number 1.6. So I already discussed with you whatever the problems given in the textbook, same numericals will not be asked, because they will change the values, but the pattern of the numericals will be same. So this numerical many times asked for the board examination. See this niobium. So we will discuss this numerical or this numerical. First, we will discuss this niobium. Niobium forms BCC structure. So already BCC is there, means there are two particles. The density of niobium is given. So the density is given. Age length is given. Then what is the question? How many atoms? How many atoms and unit cells present in 0.5 gram of niobium. So the question is, we have to calculate how many atoms and unit cell present in 0.5 grams of niobium. So first we have to write the given things. Number of atoms in x gram of niobium, x into n divided by rho a cube. This is the formula. So this formula we have to remember. By using this formula we can calculate the number of atoms. Xn divided by rho a cube. So x is equal to 0.5 grams. This is given. 0, we have to calculate the how many atoms present in 0. X gram of niobium. So x is given 0.5 grams, n is 2 because this is a body centered cubic structure. So in case of body centered cubic structure, n is 2. Then rho, the density is also given. Then age length is also given. So age length, what is the age length? In this numerical age length is given 330.6 picometer. So A is given, then the rho is also given, X is also given. So I think all the values are given of this formula. Xn divided by rho A cube. X, put the value of X here into 2 because 2 is number of particles. Then this is the density 8.55 grams per cm cube, and age length cube 3 picometer, it is converted into centimeter, 3.306 into 10 raised to 8 centimeter cube. So by solving these steps we will get the number of atoms. These are the number of atoms in 0.5 grams of niobium. So by using this formula we can calculate the number of atoms. Now another question is asked, how many atoms and unit cells. Unit cells also we have to calculate. So for the number of unit cells, this formula we have to use again, the second formula. G is equal to x divided by rho u cube. All the values are already known. This is the value of x, x into uh, yes, number of unit cells in 0.5 grams of niobium. So 0.5 grams into 2 divided by 8.52, sorry, 8.55 grams per cm cube. This is density, and this is a 3 point. Wait. Some mistake is there in the numerical because both the steps are written same. Both the steps are written same because this 2 is not required here. So remove this 2. This is a printing mistake in your textbook also. So 0.5 divided by 8.55 grams per cm cube into 3.306 into 10 raised to minus 8 cm cube. So the answer should be 1.62 into 10 raised to 21. So do the calculations at your home. This numerical can be asked for 3 marks. Remember, this is a 3 marks numerical. So this numerical we can read at your home, whatever the numericals are given here. These are all the solved numericals we can read. If you have any problem in these numericals, ask me and make a correction here, because this formula is x divided by rho a cube. You don't take here number of particles. Again, one numerical. This is a very big numerical. This can be asked for the 4 marks numerical. We will discuss when we will require the time. We will discuss at last. We will discuss all the numericals of all the chapters. These are the numericals given from the exercise. So don't worry about the numericals. All the solved numericals and unsolved numericals are also given here. We will discuss this numerical. The density of iridium is 22.4 grams per cm cube, means the value of rho is given here. The unit cell of iridium is FCC. FCC means the particles are also given. In case of FCC, how many particles are present? Anyone can tell me? Yes. Unmute yourself and tell me how many particles are present in FCC structure. Yes. Manav Jori, tell me. Manav is there? Hitesh?
What, sir?
Tell me, in case of FCC structure, how many particles are there? Number of particles, tell me. In case of face-centered cubic cell. I will give you hint. In case of simple cubic unit cell, there is one particle. In case of body-centered cubic unit cell, there are two particles. Tell me, in case of FCC structure, how many particles are present? We discuss in detail how to calculate the number of particles. In case of FCC, each particle it is shared between two faces. So 1 by 6 into 2, it will be 3 plus 4. 4 particles are present. See this, I will show this diagram how to calculate the number of unit cells. Then you will understand this is completed or not. Yes, see this number of particles. This is the number of one particle is present in case of simple cubic unit cell. In case of body-centered cubic unit cell, there are two particles. And in case of FCC, there are four particles. How these four particles? Because each particle it is shared between two cubes. So 1 by 6, sorry, 6 into 1 by 2. Because six faces are there, and each particle it is shared between half. So 6 into C here, 6 into 1 by 2, it is equal to 3. And this is one particle, it is prepared with the corner. This is a, only we have to remember the number of particles, 1, 2 and 4. So 4 particles are present in case of FCC. If you didn't remember, we can't solve the numericals, remember. So only we have to remember this 2, 1, 2 and 4. These are the particles present in simple cubic, body-centered cubic and face-centered cubic. So as it is given FCC structure, 4 particles are present. One, what is asked? Calculate the radius of iridium atom. Molar mass is given. So what we have to do? See, this formula already you have this formula, rho is equal to nm a cube divided by na. So what is the value are given? We have to write the given values. The density is given. So the value of rho is given here. Rho is 22.4 grams per cm cube. Then number of particles, n is given, because FCC is given means n is given. N is 4. Then the molar mass is given. This m is molar mass, a is edge length, and na is Avogadro's number. So All the values are given. We have to only substitute the values in this equation. So value of n is 4. This molar mass is given 192.2 here.